Hi everyone, this is Bryant. My uni is a BHZ2103, and the project that I've chosen for this semester will be a neural network-based language modeling. Okay, so to discuss this project a little bit, basically the main motivation of the project and of these types of models is automatic speech recognition, ASR for short. So what this entails is effectively basically automatic translation from spoken language, so like what I'm doing now, into text, right? So effectively like the automated captioning that you see perhaps if you're a CVN student, or something, for example, on your iPhone like Siri, or even, for example, what Alexa has to do, right? And so traditionally, the kinds of models that have been used for this task are n-gram models. And in a class a couple weeks ago, we discussed the basics of n-gram models, where basically n represents the number of words, and it's kind of like the path dependency of, and the probability of that path. Like, hey, something like I like food would be significantly more probabilistic than a chain of 3 words that people never speak in sequence, like purple monkey dishwasher, for example. Okay, but obviously, what's left out of these kinds of models is kind of the long-term dependencies of the model. So, for example, in one of the papers that I'll be reviewing for this project, the example is brought up that if somebody mentions the word Korea, for example, then the city Seoul may be much, much more likely to come up in the top of a conversation later. And especially Seoul, the city, even though it's homophone for soul, like, your spirit or your entity, even though the latter is probably more probabilistic from a unigram standpoint, Seoul, the city, would be much more probabilistic if the word Korea came up earlier on. So I'll be exploring a lot of these, what are known as RNNLMs, which is basically recurrent neural network language models. Okay, they're built off of either the LSTM, long short-term memory, or GRU architectures to try and capture that long-term dependency. Okay, and we'll basically build a few of those models, we'll train them, and we'll see how they perform relative to each other. The data set that we're going to use is the Tedlium 3 architecture data set, rather, which is double the version 2 from 2014. 452 hours of transcribed speech from TED Talks, and then kind of the performance measures that are par for the course in this realm is the word error rate, which is, it's a little bit simplified, but effectively that's the ratio of errors to the total number of words that you were trying to predict, and the perplexity, which is basically a statistical measure of how good your model predicts kind of the sample that you're trying to predict. Okay, and then so a few of the papers that we'll be reviewing and some of the ideas that we'll be reviewing, we're going to go through a glossary of models, right? We're going to go through the basic n-gram models, which that's going to be a quick, naive way to establish a baseline of performance, okay? And then we're going to use the queued RNN-LM toolkit, which presented in one of the papers is a very efficient way of training RNN-LMs, but also gives you quick ability to kind of vary a lot of the different features, right? So, for example, if you want to support for different architectures between LSTM, GRU, it supports both of those, right? Conveniently enough, it also supports the Caldi format lattices as well. So we're going to try those. We're going to try some of the different model adaptations that are presented in one of the other papers as well. So, for example, what RNN-LMs don't do particularly well is they don't take into account the current conversational context, right? So specifically the Korea Seoul example, there's a couple different techniques mentioned in one of the papers of how to capture that conversational context. And then what's additionally mentioned in one of the other papers is kind of a pruned lattice rescoring algorithm, which is extremely interesting. Which, if you look at this diagram on the right, basically how all of these models effectively work is there's kind of a first pass decoded lattice structure that's built from the immediate like speech to text decoding, right? And then after the application of a neural model, right, that's where kind of your rescored lattice happens, right? But obviously this search space of, you know, path dependent lattices is absolutely massive, right? Because every word can theoretically go to every other word. And kind of what's traditionally used to keep the search space feasible is an n-gram based approach. But this one paper presents a really interesting A-star search like a heuristic based approach. So I think I'm going to try that as well. We're going to try marrying some of these different techniques. And yeah, ultimately what we'll do is we'll measure all of the different models and the different variations of these models and the different features and their performance on this TED Talk data set. And thank you. Again, my name is Bryant. My uni is at BHZ2103.